So this is the second lecture or the last bit of probability theory that we need for the course. So we'll run through some key ideas in permutations and combinations. As I said at the start of this section of the course around probability theory, that we're basically going to barely scratch the surface of probability theory, and that goes for the last section that we're going to cover as well. Okay, so permutations and combinations are a very interesting way of counting up outcomes. So we'll talk about how to do this properly. But again, the emphasis on the fact that we build up enough of this so that we can move forward into the rest of inferential statistics. Okay, so that's the last section for chapter 3. So after this, you should be able to finish up with chapter 3 homework completely. Okay. There is going to be a second lecture on chapter 4 as well, which I'm going to post a link to. So make sure that you take a look at that as well for this week. Okay. All right. So let's talk about permutations and combinations. So before we can talk about permutations and combinations in general, we need to be able to talk about what we call a factorial, right? What we call a factorial, and n factorial, right, is just n times n minus 1 times n minus 2 times n minus 3 all the way till you hit 1, right? So if you look at this example, a 6 factorial is basically 6 times 5 times 4 times 3 times 2 times 1, right? So that's 720. So this is just compact notation to write this kind of multiplication pattern, right? Where you're multiplying by n times n minus 1 times n minus 2 all the way until 1. This is just compact notation. So when we're talking about factorials, it's just a compact way of representing this, right? Similarly, for 4 factorial, it's 4, you start from 4 times 3 times 2 times 1, and so that's 24, okay? So the one crucial thing to know is that 0 factorial is set to 1, right? Because if you think about 0 factorial, there is no way to get to 1 from 0. So 0 factorial is just set to 1, okay? So we'll go on and talk about what we mean by permutations, and then the other thing is around combinations, right? With permutation, the crucial thing is that we are going to make choices where the order of the choices or the arrangement of these objects actually matters, right? So let's take a quick example of what I'm hoping many of you have seen, a Sudoku grid, right? Like Sudoku is a 9 by 9 grid. So, there is 9 rows and 9 columns, right? So there's 9 columns here and 9 rows here. So, and inside each of this, there is again a smaller grid, right? So, inside each of these 9 by 9 squares, you can fill numbers or digits from 1 through 9, and you can't have repetition across the column or across the row, okay? So the question is, how many different ways can the first row of a blank 9 by 9 Sudoku grid be filled, right? So if I think about the first row here, the question is, how many ways are there for me to fill this, right? So the question is about counting the number of different types of arrangements that we can do. And if you think through this situation, for the first position, you have all 9 numbers available, right? So all 9 digits which are available, 1 through 9, all 9 digits are available. If I think about the second position, if I fill this with one particular digit, say I fill this with the number 1, then I can't reuse that, right? So if I use one number here, that's not available as a choice for the second position. So if I think about the second position, I have only 8 choices there, so on and so forth, right? So if I think about this, it's going to be 9, 8, 7, 6, 5, 4, 3, 2, 1. So there is 9 factors. So 9 ways to fill the first position, 8 ways to fill the second position, 7 ways to fill the third, 6 ways to fill the fourth, 5 ways to fill the fifth, so on and so forth, right? So this is basically an extension of the fundamental counting principle in a certain way, right? This is number of ways of filling the first position and times the number of ways of filling the second position times the number of ways of filling the third, so on and so forth. And we can compactly write this in this notation of what we call the factorial, right? So 9 times 8 times so on until 1 is basically, you can compactly write it as 9 factorial, okay? All right. So in the more general case, right, here there's 9 positions, we have 9 choices to make. This is basically the limiting case. What happens when you have choices to be made, right? So the most important thing here is the notation, right? N is the number of things that you can choose from, right? This is the number of distinct objects that are available to be chosen. R is the number of objects that you're going to choose at any point. So the number of objects is n, number of choices taken r at a time is r, and the p here represents it's a permutation. And remember, a permutation is where the order, let me actually switch to uh, okay, it's fine. So the crucial thing is that when we're thinking about p here, the notation, this p essentially says it's a permutation. What it means is that the order in which these R objects are chosen matters, right? So in general, the formula for NPR is written as n factorial over n minus r factorial, all right? Okay, if this seems like a little bit uh, not very intuitive, so let's take a look at an example and see why it matters, okay? So suppose you have a lock, right? It's a lock which takes in a code, and it takes a 4-digit code, right? So 4 digits code, and none of the digits can be repeated, right? No digit can be repeated. And the story is, okay, the first thing is to ask, okay, so if I have these digits to choose from, I can choose any digit from 0, right? I can choose 1 all the way until 9. Okay. So I have 10 different options to choose from, right? 10 different digits that can be chosen, right? Of which I'm going to choose 4, right? So here, if I think about my choice, I have 10 different digits to choose from. R is the number of digits I will choose. Number of positions to fill is only 4 in this case. So 10 to choose from, 4 to choose. Now the question is, does the order in which these 4 digits are chosen matter or not, right? So if I think about it, I could have two different codes, 1, 2, say 3, 4, right? That's one code, that's a 4-digit code. Or I could have, say, 4, 1, 2, 3. Okay. So if I think about these two cases, the same 4 digits are used in either code, right? It's 1, 2, 3, 4 or 4, 1, 2, 3. They have the same 4 digits. But the crucial thing is that if this is the code I set on the lock, it will open the lock. But if I enter in this code, it won't open the lock, right? In this case, the order in which these numbers appear actually matters, right? So that's what makes this a permutation, right? The order of the choice actually matters. So there's 10 objects to choose from. Only 4 of them are chosen at any given point in time, for any given instance, and the order in which this choice is made actually matters, right? So the notation is 10p4, right? So this is a case where the order of the choice matters, and that's what makes this a permutation, right? And the formula is straightforward, that 10p4 is n factorial, which is 10 factorial, over n minus r factorial. N is 10, r is 4, 10 minus 4 is 6, so it's 10 factorial over 6 factorial. If I expand this out, 10 factorial is 10 times 9 times 8 times so on until 1, and 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And then some of these cancel out, and I get basically this 5040 ways of creating a 4-digit code where all digits are available and no digit can be repeated. Okay. Right. So again, the question with permutations, well, to distinguish whether you're dealing with a situation with permutations or whether you're dealing with its other situation of what we call combinations, the essential answer comes down to, does the order of the arrangement matter? Does the order in which the choice is made matter? Okay, so this is a classic case where the choice order of the choice matters, and you have a permutation. Okay, all right. Hope that's clear. So let's look at a second example. Right? So 43 race cars started the 2007 Daytona 500. Right? There's 43 different cars that started the Daytona 500. We want to know how many ways can the cars finish first, second, or third. Right? Again, think about the choices. Right? You have 43 different cars to choose from. You have three positions to fill, right? You have a car which will finish in the first position, a car which will finish in the second position, and a car which will finish in the third position. So 43 cars to choose from. Three cars need to be chosen, right? Three cars will be chosen, and the order in which these cars are chosen actually matters, right? So if I choose a red car as the car which comes first, it can't also be the second, right? If the order is RBG, red, blue, green, if that's how they finish, then BRG is a different order, and that represents a different outcome, right? If I think about RBG, it means that the red car came first, the blue car came second, and the green car came third. But if I think about BRG, it means that the blue car came first, the red car came second, and the green car came third, and those two are different. So this is a classic case where there's 43 cars to choose from, three cars are chosen, and the order in which the choice is made matters, and that's what makes this a permutation, right? So when you're writing this notation, just keep that in mind, right? N here represents it's always going to be the bigger number. So n is the number of choices to be made. This number of choices I have. Now R here represents the number of choices to be made, and P here represents the fact that this is a permutation, or the order of the choice actually matters. Okay. Again, NPR, the formula is n factorial over n minus r factorial. So that's 43 is n factorial, or 43 minus 3, which is 40 factorial, and I get 74,046 ways. Okay. Again, always remember, when we're talking about permutation, we're talking about a situation where the order in which the choices are made actually matters. Okay. One limiting case which you should be aware of is that what if there's many of the same kind of object, right? So number of distinguishable permutations means that when there are n1 of one type, n2 of another type, and so on and so forth. So it's not that each of these are distinct, right? Each of these choices are not distinct. So there's a whole number of each kind of choice, and they're not distinguishable. So again, let's take a look at an example, and this should make sense, right? So building contractors planning on developing a subdivision, right, that consists of 6 one-story houses, right? That's how many one-story houses there are. 4 two-story houses and 2 split-level houses, right? The crucial thinking here is that all the one-story houses are alike, right? So I can't tell them apart, right? There is no way for me to tell them apart. There's 6 one-story houses which are available, and all of them are basically indistinguishable. They all look the same. This is a case where I'm going to make up 12 houses in the subdivision. So 6 plus 4 plus 2 is 12 different houses, right? So there's 12 different houses to be made. There's 6 of one kind, 4 of another kind, 3 of the third kind. So the number of distinguishable ways, right? The number of ways where they're distinct arrangements of these 12 houses is 12 factorial over n1 factorial, which is 6 factorial, or n2 factorial, which is 4 factorial, and n3 factorial, which is 2 factorial. This tells me the number of distinguishable ways. Okay, the crucial thing as to consider when you're in a situation with a distinguishable permutation is when there are many of the same kind of object available for selection, and there is no way for me to tell these objects apart, right? Because all the one-story houses are alike, and there's 6 of them. It doesn't matter whether I choose the first one-story house to put in one particular position, or the fourth one-story house to put in a particular position. They're not going to be distinguishable because they're all alike. Similarly, for the two-story houses, they're all alike, but there's 4 of them to choose from, and the split-level houses, both of them are the same, so I can't really tell them apart. So that's the case where we can find distinguishable permutations, right? And the formula, as we saw in the previous slide, it goes n factorial is the total number of objects available for selection, right? You add up all of these, over n1 factorial is the number of objects of the first kind, times n2 factorial number of objects of the second kind, number of objects of the third kind, and the number of objects of the kth kind, right? So that's how you find distinguishable permutations. Okay. All right. So if there's any questions, just make sure you leave it in the comments below the video so I can address them as we go along. Okay. I hope things are clear so far, and then we'll keep going with the material. Okay. So the other kind of counting, and this is the last thing that we'll do for this chapter on probability theory, is again selection is going to happen. So there's n objects to choose from. R objects are chosen, and suppose the order of the selection doesn't really matter, right? That's what we call a combination. So without regard to order, right? So that's the crucial element of it, is that we don't really care about the order of the selection itself. All we care about is just the blind selection. So NCR basically says there's n objects to choose from, R objects are chosen, and C here represents the fact that it's a combination, or the order in which the choice is made doesn't really matter. Right, so NCR, the formula is given as n factorial over n minus r factorial times r factorial. This is the additional r factorial which is in the denominator here. Okay, so again, all of these is well illustrated with an example. So let's take a look at one. A state's Department of Transportation plans to develop a new section of interstate highways, and there's 16 bits to choose from. Okay, so there's 16 bits which came in. So in this particular case, straight away you can tell that n is 16. There's 16 bits which came in, of which you want to hire 4 of the bidding companies, right? So again, you need to choose or select 4 companies from a group of 16. There are 16 companies which are to choose from, 4 companies which are chosen, and the order of their choice doesn't really matter, right? It doesn't matter whether I give the first contract to the first company or the first contract to the third company. The contracts are the same. The order in which the selection of these companies happens, it doesn't matter when the company is chosen, as long as the company itself is chosen, right? So this is a classic case where in the selection criteria, the order of the selection doesn't really matter, right? So this is what we call a combination, right? So there's 16 bits to choose from, of which 4 are chosen, and C here represents the fact that the order of the selection doesn't matter. The order is not important, there's no regard to order, so it's a combination. So we write this as 16C4, which the formula says is 16 factorial n factorial over n minus r factorial, 16 minus 4 factorial times r factorial, which is 4 factorial. Right? So 16 factorial over 12 factorial times 4 factorial, you run the math on that, and you get 1820 different combinations. Right? So between permutations and combinations, it's always we are going to make a choice, right? And the question always boils down to, does the order in which the choices are made matter or not? If it does matter, it's what we call a permutation. If it doesn't, that's what we call a combination. Right? So again, if there's any questions, the comment section is your best bet to get a quick answer. But the point of all of this is not to just do this counting. The counting itself is relevant, but the crucial thing is about finding probabilities. So let's take a few examples on how to use these ideas to counter probabilities, to find probabilities. All right, so here's the setup for the first example. So a student advisory board consists of 17 members, right? 3 members serve as the board's chair. So the 17 members who are available for choosing, and you're trying to select for 3 positions: chair, secretary, and webmaster. Right? What is the probability of selecting at random the 3 members that hold each position? Okay. So the first thing is to ask, how many ways are there for me to form a board of 3 members, right? How many ways are there for me to form a selection out of the 17 members who are available? How many ways are there for me to choose for the 3 positions that are available: chair, secretary, and webmaster? So if I think about this, there's 17 members that I could possibly choose from. I'm going to choose 3 of them, and the order of the selection actually matters, right? If I choose one person first, that person becomes the chair. The second person I choose becomes the webmaster, and the third person I choose becomes the secretary, right? So the order in which these three people are chosen actually matters, because the order in which I choose them determines what position they occupy. So this is a classic case where the order of the choice matters, right? 17p3. So 17 members to choose from, three of them are chosen, and the order in which they're chosen matters, and this is a case which we call a permutation, right? So if I think about 17p3, it's n factorial over n minus r factorial, so 17 factorial over 17 minus 3 factorial, or there's 4080 different ways of filling out these three positions from the available 17 members. Then the probability that you end up with the board that you do have is the number of ways I can make boards versus number of ways which satisfies the conditions of being my boards. So I have one uh, constitution of my board. There's 4080 different ways I could have come up with it. So the probability that I end up with my particular board is 1 over 4080. Okay. So again, remember the crucial thing here is to count up the number of outcomes. So there's 17 members to choose from. 3 of them are chosen for these positions, and the order in which the choice is made matters, and that's what makes this a permutation. Okay. All right. So let's look at a couple more examples. You have 11 letters. Okay. You have 11 letters to choose from. You have one M, 4 I's, right? 4 S's, and 2 P's. Okay. So you have 11 letters in total to choose from, right? You have one M, 4 I's, 4 S's, and 2 P's. The crucial thing to recognize is all these I's are alike. An I is an I, right? So you have 4 of them. Whether which I goes where is irrelevant. So this is a case where I'm going to arrange 11 letters in random, but I have many of different kinds, right? So this is a case where I have distinguishable permutations, right? So I have 11 factorial ways of choosing. There is one way of choosing an M, 4 different I's to choose from, so that's 4 factorial. There's 4 different S's to choose from, that's 4 factorial again, and then 2 P's to choose from, 2 factorial. So this is the number of distinguishable permutations where I have 11 letters with 1, 4, 4, and 2 like letters. Right? So the number of distinguishable permutations in this case is 34,650. Again, remember, the crucial thing is that you're arranging all 11 letters, but you have many of the same kind. They're not distinct objects, there are many of the same kind, so you want to find distinguishable permutations. Right? So there's 34,650 different permutations that you can make using these 11 letters which are available to you, of which only one of them is the word Mississippi. So the probability that when you arrange 11 letters in a random order, the probability that you end up exactly arranging them in this order of getting Mississippi is 1 over all the possible different ways you could arrange the 11 letters, 34,650 ways. So this is the probability of just randomly taking these 11 letters, putting them on the table, and then they are arranged as Mississippi. Okay. All right. Hope that's clear. Again, if there's any questions, again, please feel free to ask. All right. So the last example that I want to deal with here is about finding probabilities in this case. Right? A food manufacturer is analyzing a sample of 400 corn kernels. Right. So again, there's 400 different kernels which are available to be chosen from. Right. And you're going to test for the presence of a toxin. In this sample, 3 kernels, we know the 3 kernels have dangerously high levels. So there's 3 of them which are very dangerous. And so that means that there's 397 which are not dangerous, right? So if 4 kernels are chosen randomly selected from the sample, what is the probability that exactly 1 kernel contains a dangerously high level of the toxin? Okay. So if I think about this, right? So I'm going to choose 4 kernels, right? So I'm going to end up with choosing 4 kernels, right? So because 4 kernels are randomly selected. So R here is 4. Okay. So what is the probability that exactly 1 kernel of these 4 contains a dangerously high level of the toxin, right? So let's think about the toxic kernels, right? So there's 3 of them. there's 3 toxic kernels. I need to definitely choose one in my sample. So, and the order in which I choose doesn't really matter, right? It doesn't matter which of these 3 I choose, first, second, or third, whatever it is, it doesn't really matter. All that matters is that I choose one of them. So this is a combination. So I have 3 kernels to choose from. One of them is chosen, and the order in which I choose it doesn't really matter. So there's 3 different ways of choosing the toxic kernel. So the other 397 kernels are non-toxic, right? To form my sample, of this 397 kernels, I need to choose 3, because together I need a sample of 4 kernels, in which case I need 1 from the 3 toxic ones and 3 from the 397 non-toxic ones. So the number of ways I can choose 3 non-toxic kernels from 397, in which case the order again doesn't really matter. It doesn't matter how I make these choices. So I have 397 non-toxic ones to choose from. I'm going to choose 3, and it's a combination in the sense that the order in which I choose them doesn't matter. Okay. So from this, I know that there is 3 ways to choose one toxic kernel, 10,349,000 so on ways of choosing a non-toxic kernel. So if there's m ways of choosing the first one, n ways of choosing the second one, there's m times n ways of choosing this sample. Right? This is basically an application of the multiplication rule. It says that if there's 3C1 ways of choosing the toxic kernel, 397C3 ways of choosing the non-toxic kernel, then there's a 3C1 times 397C3 ways of choosing a sample of 4, which consists of exactly 3 non-toxic kernels and 1 toxic kernel. Right? This tells me the total number of ways I can get my particular kind of sample of 4. Okay. So if I want to find the probability, right? If I choose randomly, if I'm not looking for a specific sample which consists of 3 non-toxic and 1 toxic, if I'm just going to choose at random, I have all 400 kernels to choose from. I'm going to choose 4 of them at random, so the number of ways I can choose 4 random kernels from 400 possible ones is 400C4. Okay. So the probability of selecting exactly one toxic kernel is the number of ways I can select exactly one toxic kernel, which is this, over the number of ways of forming samples of size 4 from the available 400 kernels. Right? So this is the size of the event space. This is the size of the sample space. Again, the ratio is going to tell me the probability, and the probability here is about 0.0296. Okay. Again, the homework has enough questions to give you practice on these ideas. I hope that gives you a bit more here, because this is one of those topics in statistics which you get better at once you see more and more different types of questions and different types of situations, and the homework is really going to gear you up for that. All right. So that's it for chapter 3. So we'll stop there for this particular lecture. And then what we'll do is I'll post a second lecture covering chapter 4, and I'll post the homework as well, and we can discuss ideas after that. So if there's any questions, make sure that you leave them in the comments below the video, and then I'll see you in the next one. All right, take care.